In this lecture, we'll discuss the ANOVA table and the general linear f-test, which is going to be a big test that we take advantage of both in this section and certainly later on when we get to more complex linear models. First, though, we're going to talk about the Hotelling confidence band, and then we're going to move on into the ANOVA table, which extends into the general linear test. The working Hotelling confidence band gives a confidence limit for the whole line at once. Now, if you think about the confidence interval for the mean that we discussed in the last lecture, the confidence interval for the mean calculated the confidence interval for a single point. However, if we want to calculate confidence interval for multiple points, then we have to use a different statistical calculation to take into account the fact that we're calculating multiple confidence intervals at the same time. So remember, b0 plus b1x, this is the formula to get the predicted y or the average y or the expected value of y for the value of x sub h. So if we're looking for a confidence limit for the whole line at once, x sub h is going to be all possible x values. We have the 100 times 1 minus alpha percent confidence interval for this pertaining to a specific x sub h. But what we want to do is, again, do this for all x sub h's instead of just for a single x sub h. So in the last lecture, we discussed how to do this confidence interval for the mean for a specific x sub h. Now we're going to talk about how to do it for all x sub h's at the same time, and that type of band is called the working Hotelling confidence band. Note that we can calculate confidence bands without this adjustment. The problem is something called multiple comparisons, where when we're doing multiple different comparisons at the same time, the statistical error, this alpha, increases with every additional comparison that we do. The working Hotelling confidence band accounts for this increase in error rate as we do multiple tests, and literally every test that we add on adds the potential for more and more error in the family-wise test rate. So the working Hotelling confidence band adjusts the alpha to take advantage of that through using a slightly different statistical calculation. The confidence limit is given by exactly what we're used to seeing, the point estimate plus or minus the critical value times the standard error. What you'll notice has changed is not the point estimate, it's not the standard error. The only thing that changes for the working Hotelling confidence band is that we use a different statistical distribution to draw the critical value. That is, in this case, we use the W statistic, where W is the square root of 2 times f of 1 minus alpha with 2 degrees of freedom in the numerator and n minus 2 degrees of freedom in the denominator. So this may or may not be your first exposure to the F distribution. I think you've probably seen it before in previous classes when you've discussed ANOVA. But in the F distribution, we have 2 sets of degrees of freedom. So 2 is going to be the first degrees of freedom, and n minus 2 is going to be the second degrees of freedom. And then we still have that alpha value that we look at to determine the level of statistical significance. Now, since we're doing this for all of the x sub h values at once, this interval will be wider than the traditional confidence interval. So again, what we're doing is we're saying that the error rate is much higher than what we normally think if we calculated these using our classic formulas, if we calculate multiple confidence intervals or a confidence interval at multiple x values. So with this adjustment, we are decreasing the error rate, but the only way that we can decrease error is to make a wider confidence interval. So we decrease error by making a slightly wider interval. So our confidence limits from the working Hotelling band are going to be slightly wider than the confidence intervals, and this is to adjust and make sure that we are taking into account the appropriate amount of potential error that happens when we increase the number of tests. So to fill in these different elements, I wrote the general format, but again, we kind of can write that almost without even knowing what we're doing. However, it's tougher to fill this in. So let's go on and fill this in. What is y hat sub h? Well, that's just the prediction at the value of h. And recall, h is going to be all of the possible x values. W is that statistic we looked at earlier, and then we had the standard error of y hat. That's the MSE. This is the predicted value for sigma squared times 1 divided by n plus x sub h minus x bar quantity squared divided by the sum of squares of x, or the sum from I equals 1 to n of x sub I minus x bar quantity squared. So this is just the sum of squares of x that we had from our, if you go to the previous lecture, you'll see that this was the standard error for y hat sub h. That was the mean, the confidence interval for the mean prediction error. So if we're looking for the prediction for the mean, this was the standard error of that prediction. Note that x sub h, again, represents all of the x values that we're interested in predicting. And again, when we're using the working Hotelling band, the concept is that we are interested in predicting a confidence band at multiple x values. So x sub h is for each one of those multiple x values that we're interested in. If we were just interested in predicting for a single x value, a single x sub h, we would use the classic confidence interval formula. Also note, sometimes this gets confusing, but these x's in the denominator here, this is the sum of squares of x. So this has nothing to do with x sub h. This is just the sum of squares of x. So don't get confused. We've got x sub h here, x sub h minus x bar, all this other stuff. And it's done for all the different x values. This doesn't change. So it doesn't really matter what x value we're looking at a particular time. This denominator is a constant. That denominator is the constant sum of squares of x. Also note that this adjustment is used for estimating the confidence of the means of the lines at once. So this is for all of the particular lines that we could be looking at, and we can estimate the confidence for all of those lines. And if you think about when this is necessary, if we're looking for a wide variety of different predicted values, or if we're looking for a general confidence for each potential point of the mean, we're looking for the confidence of the line, this could be a necessary component that we would take advantage of. So in practice, how do we actually do this? And I think one of your homework problems is going to give you the opportunity to practice constructing these by hand. I think in our R example, we'll talk through just how do you do this with a regular confidence interval. I think in last lecture's R example, that also demonstrated that. So both of these are good ways to demonstrate how you could work through this by hand. Though in the last lecture, we used a predict. That's not going to work for the working Hotelling band because we don't want the confidence interval. We don't want the prediction interval. We want the working Hotelling interval, and that uses that W statistic. So if we're using this for a predetermined set of values, that is, we want to calculate confidence intervals for these 10 specific x sub h values, then we find the value of W using the F distribution, and we just plug those 10 h values into the equation, and we have those 10 intervals. Now, if we're doing this for all values in a range, think about it, if we're doing this for an infinite number of x values, I can't just make a table to demonstrate what each of the confidence intervals are for every possible value of x. There's an infinite number of them. That would be an infinitely long table. So how do we display this for an infinite number of x values? Well, you probably never thought about this before, but graphics are the way in which we can display, and a continuous line is the way in which we can display intervals for literally an infinite number of x values. So if we want to do for all of the x values in a particular range of x values, we would use a graphic to display the infinite number of confidence intervals that we have. First, we create an ordered list of x values that span the given range. Now, this is very important. One of the biggest frustrations that students run into when they try to create working Hotelling intervals in like a homework problem is that they use an unordered list of x values. Note that this is not the x values. This is not the observed x values from your data. What we do first is we create just a list of x values that span the range of the observed x values but aren't necessarily them. So if my x values go from 0 to 100, and let's say the x values are 0, 26, 37, 58, and 100, then I'm not going to use just those x values. I'm going to create 0 to 100, and I'll look at every single number between 0 and 100 and calculate this interval, because again, I want to create an infinite number. I want to create a whole bunch of values in this range and calculate the interval for all those. That would be super annoying to do by hand, but on a computer, it goes very quickly, and it's worth taking the time to do this well, because again, we're using this to estimate an infinite number of x values. So this ordered list, this is our pseudo infinite number of x values. You don't actually have to use an infinite number of x values, but we will have a lot more x values than are usually in our data set, and that's because we're trying to graph a line or a curve as opposed to just look at a specific predetermined set of x values, which is also possible. It's just not what we're doing in the second option. After we have each of those x values that we're going to use to plot, and sometimes I'll call them plotting x's or px's, just because to distinguish them from the actual observed data values that I have, my x data values. Then I'll calculate the upper and lower working Hotelling band for each of the x values, and I will plot the upper and the lower bands for the value. So I'll go through each one of those x values and I'll plot the upper bound, and then I'll go through each one of those x values and plot the lower bound using that lines command, and that's how we will get the plot of an infinite number of x values in a range. It's pretty cool that we can look at an infinite number of x's and do an infinite number of calculations on our computer. Well, kind of. All right, this has been discussing how to do the working Hotelling confidence band. In the next video, we'll jump in and start talking about the ANOVA table for regression.